So, if we have two sets of complex coefficients, gamma sub alpha and L sub alpha, such that their norms squared summed across A are finite, then we can apply the parallelogram law, proposition 3.11, as follows. So, if I take a vector of the form gamma sub alpha E sub alpha plus L sub alpha E sub alpha, norm it, and take the square, this is going to be equal to gamma sub alpha plus L sub alpha, because, again, the E sub alphas are a orthonormal subset. So, naturally, I'm going to get that the square of this sum, the norm of this sum here, is going to be less than or equal to the sum of itself plus gamma sub alpha minus L sub alpha normed squared. This, however, by the parallelogram law, is going to be equal to 2 times the norm of gamma sub alpha squared plus 2 times the norm of L sub alpha squared. By hypothesis, however, we know that these two summed across A are finite. This gives us that the sum, alpha and A, of the norms of the vectors of this form, gamma sub alpha E sub alpha plus L sub alpha E sub alpha squared is also finite. So, this gives us vector addition because if F and G are elements of N, then F is equal to some sum, alpha and A, of gamma sub alpha, E sub alpha, and G is equal to some sum, alpha and A, of L sub alpha, E sub alpha. Now, I can say if we consider F plus G, this is going to be equal to, again, we're going to use the definition of a sum across an infinite set. So we have that this is equal to the limit f in curly f of the sum alpha in f of gamma sub alpha E sub alpha plus L sub alpha E sub alpha. And the reason that I can do this is because I can split sums across limits, and because f is finite, these are finite sums, so I can rearrange my terms as I please. But this is by definition just the sum of alpha and A of this inside here. So gamma sub alpha E sub alpha plus L sub alpha E sub alpha, which we get converges. By our below argument here, we get that the sum of the norm squared is finite. So this one here is convergent, so N is closed under addition.